Bismillahirrahmanirrahim. Today is lecture number 4, Aashto method of flexible pavement design. And we will discuss what are the material properties that are needed to design a pavement. In the first lecture, I have discussed there are 4 layers of asphalt pavement. They are asphalt bearing course, asphaltic base course, crushed aggregate base course, air granular subbase course. Normally we do abbreviate them as A stand for asphalt, W for bearing, C for course, asphalt, A, base, B, C course, C, crushed aggregate base course, and granular subbase course. Remember, each layer on asphalt is termed as course. Now, one of the property that we need to design a pavement by Aashto is a layer coefficient. This is typically abbreviated as small ai. What is a layer coefficient? Layer coefficient is actually a layer structural coefficient that represents how much this layer will act as a structural element. Remember, asphalt contract, asphalt, asphalt concrete is not a asphalt concrete is not a structural material like cement concrete. So we believe that 40 to 44% asphalt concrete behave like an asphaltic viscose. So we adjust the depth accordingly, or we say we improve or we extend the thickness based on this layer coefficient. The elasticity modulus is between 400,000 to 450,000. Remember, on asphalt bearing course, it is not an elastic modulus, it is a resilient modulus. Asphalt is to believe, asphalt cement concrete is believed to have be a viscoelastic plastic material. That is, it behaves both like a viscous material, that is, it flows with temperature. Sometimes it is recoverable, and part of it is not recoverable. So that's why called plastic, viscoelastic plastic material. Normally, the elasticity modulus we need, we take for asphalt bearing course is between 4 lakh to 450, 4.5 lakhs. Now, the same goes with an asphaltic base course. The difference between asphaltic bear course and asphaltic base course is the size of aggregate. Normally, the size of aggregate is more larger than the asphalt size of aggregate we use in asphaltic bear course. So again, we can take the same property because it is also an asphaltic base concrete. The third layer, we call this as crush aggregate base course. It is not binded and the layer coefficient is 0.14 and the elasticity modulus, it varies from 25,000 to 30,000. Also, we define the properties of crush aggregate base material in terms of CBR. Normally, when we design a pavement, we say 8 CBR, any material that have got CBR value of 80 can be used as this crushed aggregate base course. Then we have a granular subbase course. The normal values are between 12,000 to 15,000 and it has a CBR, minimum CBR of 30 we prefer to have while using aggregates in this layer. Then another property that we need to understand is the drainage coefficient. Remember, in the first two layers, we do not consider any layer, any drainage coefficient, because we suppose that all the layers are impermeable and they do not allow water to percolate through it. That's why we do not consider. While we want water to percolate from this layer, and that's why the normal range is 0.8 to 1.2, and this depends upon the area where you are constructing a road. For instance, if you're constructing a road in desert, it takes around 1.0, and when you're constructing a road near a shoreline, near a water course, then you can take 0.8. It also depends upon the quality of drainage that you are providing to the pavement. If the quality of drainage is very good, then you can go up to 1.2. But if the quality of drainage is less, then you can go for 0.8. Remember, this 0.8 will increase the thickness of the pavement, while 1.2a may decrease the thickness of the pavement. Normally, it's safe to use any value or maybe a value of 1.0, but again, I just keep on repeating, when you are doing asphalt pavement near a coastal line or near any water body, take it 0.8. So these are the material properties. Now let's move ahead. Finally, we will know how we calculate the thickness of each layer in Aashto Flexible pavement design method. Thickness calculation. For thickness calculation, actually we calculate structural number. So structural number is actually, it is related to the actual thickness of the various layers of the pavement. So it has three components if it has got three layers. And if it is have four components, if it have four layers. Now you can take the first two layer of asphalt, an asphalt surface that contain asphalt wearing course and asphalt base course. This is structural layer coefficient that I have discussed, value 0.40 to 0.44. D1, we are interested, that is the thickness of the surface layer. A2 is the drain. A2 is the structural layer coefficient, and this is for crushed aggregate base course layer. D2 is the thickness of crushed aggregate base course that is required for this pavement. M2 is a drainage coefficient. Remember, in the last slide, we say it is 0.8 to 1.2. And similarly, the last expression, it is again structural layer coefficient, value of 0.10 to 0.12. D3 is the thickness of the crushed aggregate base course or granular sub base course. We are interested in knowing its value, and M3 is the drainage coefficient, again 0.8 to 1.2. The structural layer coefficient can also be calculated using the elasticity of base. Remember, for crush aggregate base course, we said that this can be, elasticity of base can be with around 30,000. So we can use 30,000 here, take the log, multiply it, and you will get 0.97, and minus 0.977, you will get around, for 30,000, you get around 0.14. Similarly, for knowing the structural layer coefficient, you can use elasticity of subbase and then you calculate. For the sake of this class, you can only remember the values of 0.104 for A3 and 0.14 for A2. Now, so as I discussed, D1 is the thickness of surface course. D2 is the thickness of crush aggregate base course, and D3 is the thickness of sub base course. There is obvious, then there will be what we call a compacted subgrade, that we can say this is road bed course. Now, what we do, we can calculate thickness of D1 by using this relation, SN1 asterisk, and then first we calculate D1 asterisk, and then we will confirm this. I will show you in the example how you do it. For calculating D2, you remember this formula, SN2 minus SN1 up over A2M2. Again, we check it. And then D3. So the design criteria is satisfied if all these SN we have calculated should be less than or equal to the SN that was required. Now, we take the design example. Using the Aashto Flexible pavement design procedure, design a pavement for a rural interstate or a motorway highway. The expected traffic is 13 million vehicles. The pavement structure is to be consist of an asphalt concrete with an elasticity modulus of 400,000 psi. Asphalt base course with an elasticity modulus of 300,000 psi. A granular base course with an elasticity modulus of 26,000 psi, and a granular subbase course with an elasticity modulus of 12,000 psi. The CBR of the soil subgrade is 5. Assume drainage coefficient of 0.9. Assume that a reliability level of 90% is required, and that initial serviceability is 4.2 and the final serviceability is 2.67. Use the nomograph to determine the structural numbers for the various layers. This requires value for reliability, standard deviation, W18 means easels, resilient modulus, and delta PSI. Now, what are the solution steps? First, we are going to populate for the design input. The first parameter that is required in Aashto method is serviceability. It is defined in terms of PI and PT. Both are given in the problem. So what we need to do is just calculate delta PSI, that is change in PSI, EI minus PT, and it comes out to be 1.5. Then gravity and standard deviation. Reliability is 90% as stated in the problem, and while discussing the Aashto method pavement design, we know that standard deviation value is typically taken as 0.45 of flexible pavement. The third parameter is traffic in terms of easel, and that is also known to us, that is 30 million. Now, for subgrade, we have been given CBR5, and then we can convert subgrade into resident modulus by using this relation MR is equal to 2,555 times CBR 0.64. So that comes out to be 7158 PSI. Now, another design input is the material property. So what we do, we take down all these values, and as I've discussed, we'll take 0.40, 0.35, 0.14, 0.10 as structural layer coefficient, 400,000, 300,000, 26,000, 12,000, all of them have been given to us, and the drainage coefficient 0.9 is already available to us in the problem statement. We need to calculate SN value. So first, you will use this chart. This is known as nomograph, and it has got various parameters here: reliability, standard deviation, then there's a transfer line, then this is a logarithmic scale of W18 equivalent single axle load application, and remember the limit, it's 50 million. So if you come up with a traffic more than 50 millions, we cannot design Aashto flexible pavement using Aashto method. Then there is an effective roadbed resilient modulus, this value, and this is a delta PSI chart, and we will know how and I will show you how you use this nomograph. What we do first? First, we locate our design parameter. Our reliability is 90, so we put 90 over here, and then the standard deviation is 0.45. So what I've done is I've connected 90% to 0.45. I have drawn a straight line and I've rested to this transfer line. So what we do, you locate these parameters on the graph and then join these 2 points and extend the line. So there, now we are standing here. Now we had an E cells of 13 million. So what we do, so this is 10, this is 20, 30, 40, 50. But remember, this is a logarithmic scale. So you have to be, you know how to read this logarithmic scale. So this 10, 20, 30, 40, and 50. And since our 13 come between 10 and 15, so we will take any value between here. So this is how I have done. Now, once I've located this, then we join this value with the value. Now again, this is 1 point, this is second point. Again, I have stopped into at this point. Now, after this point, we'll use 3 resident models because we have 3 layers in a asphaltic pavement that we are designing. For surface, we'll take 30,000. For defining the asphaltic surface course, we'll take 26,000 value, and we will stop. We'll connect this value with the transfer line and we'll stop here. To know the structural number of crush aggregate base course, we'll join 12,000 with this value, and then we connect from this point. And then we go perpendicular, locate 1.5 here, and then we go straight to know the structural number value. Similarly, for knowing the thickness or structural number of granular subbase course, we'll use resident modulus of soil, that is 7158, connect with the traffic line. Again, we go perpendicular from this graph, and from 1.5, this is P delta PSI will go 90 degree, and we will read these values. If we will have more layer, for instance, if we had 4 layers, then we could have designed, connected this resilient modulus with this line. So remember, till this point, we must have a same line, but after this line, we may have 3 branch line. The first branch line is for knowing the structural number of an asphaltic surface course. We connect this point, extend this point to this y-axis, and then we go perpendicular, locate 1.5, that is the terminal serviceability, and then we go perpendicular. Similarly, for knowing the structural number of crush aggregate base course, we'll again we'll use the value of elasticity modulus of granular subbase course. We join these 2 points, stop here this y-axis, go perpendicular, touch the required curve, and then we go perpendicular. And for granular surface course, this is the last line. And then once you know it, then again you will read this value. For instance, this is 3 and this is 4, right? So you will know that your structural number is between 3 to 3.5. That's why I say this is 3.4. It can be an approximate value. Now, what we do, we have this 4 and this is 5. So we say this value is 4.5. That's why the SN2 value is 4.5 and SN3 value is 5. As you can see here, it's directly on the 5. One check is that this structural number 3 carries all the layers. So SN3 will always be greater than all the values and SN1 will be lesser than all the values we will calculate. So this is how structural number is calculated using nomographs. I hope you have understand, and this is very easy. It's just you have to know these values, locate those values and keep on working. Now, once you have calculated SN, then you will calculate the thickness value by using this relation. For D1, simply SN1 over A1 and this comes 8.5. Remember, whatever value we have, we have calculated for the sake of a factor of safety, we increase it by 0.5. So we have calculated 8.5. We will increase by 0.5 and it becomes 9.0 inch. Then we again calculate SN1. So 0.40 into 9, this becomes 3.6. Since we have calculated original as 3.4, we have now provided thickness of 9 inches, so it becomes 3.6. And this is the requirement that SN1 asterisk, that is SN1 provided, should be greater than SN1 calculated. And this is how this value is 3.6 and it is obviously greater than 3.4, so we can proceed ahead. If you don't find this value, even by rounding this to 0.5, then you further increase 0.5. Keep on increasing till you get this value greater than this value. Normally, it doesn't happen. It's very rare that once you round that to 0.4 inches more, it should give you this value greater than the required. For D2, you have to use this relation SN2 that was calculated. Now, here we'll use SN1 provided, subtract it, divided by A2, M2, and this comes out to 7.93. Now, you again increase it to next 0.5 inches. So, obviously, this 7.93 inch becomes 8 inches. So, again, we will like to know what is SN2 provided. We will use the same relation, and as expected, it is 4.61 and the value we required is 4.5. So the thickness of crushed aggregate base granules calculated is satisfactory. Last but not least, we will be interested in knowing SN3 as D3 value. Again, we will use this relation. It comes out to 4.3. We round it to next value of 4.5 inches. Calculated SN3, and you will find this becomes 5.02 greater than 5. Even if it is equal, then we'll go ahead. So finally, we have designed a pavement. Our pavement will consist of 9 inch of an asphalt concrete. course. Obviously, this will be there will be 2-inch asphalt bearing course, 7 inches of asphaltic base course, 8-inch of crushed aggregate base course, and 4.5-inch of granular surface. Now, once you know the thickness of the pavement that is required, you will draw it graphically, or you have to produce a working drawing showing this thickness. This is how the drawings are made. This is a typical section of an asphaltic concrete. We have assumed there are 2 lanes, there are 12 feet in each, then there is a shoulder, 6 feet, then there is a median, and the, this reflected image goes on the other side because it's a it's a 2 lane, it's a 4-lane highway, divided highway, 2 lane here, 2 here, and then there are shoulders, inner shoulders and outer shoulder. So the first layer, this first layer we'll say is the surface layers, as we have calculated, 9-inch thick asphaltic concrete. The second layer is 8-inch, and the third layer is 4.5-inch. And last but not least, these are complex. So this is how a typical section of asphalt concrete pavement is drawn. So this concludes our discussion on the design of asphaltic pavement using Aashto method. Now, there's a home assignment, and this you have to do. And this is the data. This is the data for traffic. First, you need to calculate the E cells, as we have discussed in lecture 2 or lecture 2 or lecture 3, lecture 3 probably. And then you will design a flexible as we have discussed. Now, we will use, now we will actually know how to design the Aashto method, rigid pavement using Aashto method. So, as you know, that rigid pavement consists of surface course, base course, sub-base course. These are both are optional, and there is a subgrade. Again, like, but there are different terminologies associated with the rigid pavement design. Instead of SN, we take D as the slab depth, and this is an abstract number expressing structural strength. Another terminologies that is different is we use PCC, modulus of rupture. It is a measure of flexural strength of Portland cement concrete. Usually it is 600 and 850 psi, but practically we take 650 psi. In rigid pavement, we have a drainage coefficient as well, but this is now abbreviated as CD, drainage coefficient, and we take as 1, irrespective of the pavement area we were constructing. So just take it 1.0. Then there is a load transfer coefficient. This accounts for load transfer efficiency. Remember, in the first lecture, I've said that asphalt cement concrete need dowels to transfer the load across the joints. So this is, if you have not provided this, you can take 3.8, and for jointed plain concrete pavement, and 2.3 for continuous reinforced concrete pavement with tight shoulders. Tight shoulder means the rolled shoulders are somehow connected with an rigid pavement. Another terminologies, these are elasticity modulus. We have this is elasticity modulus of concrete, and you can understand this becomes 10 times that of an asphalt concrete. An asphalt concrete we are using 400,000 psi. Now we will use 4 million psi, and the strength of the subgrade will be now taken in terms of modulus of subgrade reaction, that will be abbreviated as K. It is between 50 and 1000 psi per inch. Now, what are the considerations? Likewise, in Aashto flexible pavement design, we have following consideration: pavement performance, traffic, roadbed soil, slab characteristics, environment, reliability, D instead of structural. Now we will discuss it one by one. Serviceability, like here, 0 to 5, PI initial serviceability. Now for rigid pavement, it is 4.5. Why it is 4.5? Because rigid performs better than asphalt concrete pavement, and we take 4.5 from a scale of 0 to 5. We say 4.5 is initial serviceability for rigid pavement. Again, the terminal serviceability, the guidance are same. You can take 2.5 or 3 as terminal condition at the end of the design. So this is the typical graph that we have discussed previously in Aashto flexible pavement. So this is delta PSI, P naught minus PT. So if it is 4.5 and PT is 2.5, this value becomes 2, or 4.5 minus 3, that is 1.5. This is how serviceability is taken in Aashto. It's just like say the same we have done previously in flexible pavement design. Now, the subgrade and subbases. Remember, here subbase is the same as base in asphalt concrete in pavement. That is, what happening here is that all the rigid pavement slab, this concrete slab, is resting on the subbase. You can call it subbase, you can call this crush aggregate base course. It doesn't make any difference. So this is the dowel. These are the joints between the pavement. I have discussed if it is JPCP, it is around 15 to 30. And for a CRCP, we don't have this joint. Now, this subgrade is a compacted subgrade, and this we will take its value in terms of K. So I think we stop here, and this is the lecture number 4, and the next lecture will discuss how subgrade and other parameters are calculated, and finally we will come up with the design example and will conclude this pavement design using Aashto methods. Thank you very much, and good luck. We'll see you again. Allah Hafiz and